Okay, so we will take in the last example, and in this example, let me call a standard robot, and because I don't have it physically, I'll have to call it in a simulation framework. So all I did was to look into all the robot options, and I filtered by whichever robots were compatible with the version of ROS that I am currently running, and I got an excellent robot called as Turtlebot3. Now, some of the robots that you like may not be available in ROS, which is a rarity, but some of the robots that you absolutely love will not be compatible with your version of ROS, maybe with the older one. ROS is getting updated extremely rapidly, and they come with new versions, and robots cannot be updated at that rate. You may not be able to downgrade your ROS because you may be running a Ubuntu, and that may not support the version of ROS that you want to run. So somehow, if you get Ubuntu version, ROS version, and your robot version as matched, and you get your favorite robot, so let's just run it on the simulator because I don't have the physical real robot. So it's Turtlebot3, and let me run it on a simulator which is Gazebo. And I don't want to drag and drop and make a world, although I can. So let me launch the one which comes with a environment for itself, and I say launch. This one is a little problematic because there are three turtle bots and it's asking you which one do you want to use. So let me use the first one that's from the list. So it takes it from the environment variable. So I'm setting a environment variable just telling which robot do I need. Now let's run this and hopefully it should work. Yes, it does work. So that's your robot. Now that's what's a physical world. It's a simulator. It's the closest to reality. So it's a simulated world. Let me just improve its sizing factor so that we can see. Yeah, that's the one. That's my robot. It's an interesting robot. What does it come with? So let me inspect ROS topic list. So it's taking inputs from here from the command velocity, which is how I'll move this robot soon. And it's giving me sensor outputs, and all this is standard gazebo information. So now what's the first thing that we do whenever we get a robot? We run a slam over it. Remember, this is not the thing which is in the robot's picture. This is not known to the robot, so the robot will have to do its own slam. Treat it like a physical environment, treat it like my robotics laboratory. Let me see if it comes with a slam module. So I'm just searching for whatever using double tab, whatever the manufacturer has provided me with. So yes, there's a slam module, so let me just run it, and I just say default slam. It'll use gmapping as a slam method, and let's see what happens. The same thing. If I really wanted to run this robot for research purposes, I would have had this environment variable set in my .bashrc, but then I'm only doing it for this code, so I might actually uninstall it right away. So yes, I can run launch. That's what the robot is seeing, and it knows only this part of the map because it's sending laser beams. It's coming back. So this green is the laser beams. The gray is what are free areas, and the dark gray are unknown because the laser beam cannot see outside obstacles. So it knows this part of the map, but it needs to And it's actively running Slam in the background. So I need to move this robot, and I need to really see if it's doing Slam. Let me just see what all is going on. So I do a ROS topic list. And now you see that you've got some things about the map as well. So you've got lots of topics. If you like it, you can also look at RQT graph, which is typically what I do whenever I run everything up. So just look at the RQT graph. So you can see that there's a gazebo GUI. So that's a simulator, but then it interacts with this gazebo, and that's the mapping module. That's the transformation that it needs. So currently only the transformation information is going around. Now this LAM will of course work. This G mapping will work. It will get the position. So let me go side by side. Let me show you at one side what is known to the robot, and at the other side what is the physical reality. They may not match. For slam errors, they may absolutely not match. You see it a little slow because Gazebo is a extremely computationally expensive simulator. It runs the physics engines which compute all the dynamics of every part that you can see. It's a lot of computation. So, and I have a laptop grade system where I'm running a video recorder. It's actually a virtual box. I didn't want to run Linux because then my video recorder, I would have needed to master a new video recorder. So that's a world, and that's what the robot has in its mind. Now I need to really move the robot, so let me see if there's a teleoperation, and that's exactly what we do. We try to see if I can teleoperate a robot. So I can always call the standard teleoperator, but let's see if the manufacturer has provided me with a better teleoperation, or maybe with just a teleoperation. So is there a teleoperation? Yes, there is. There's only one, so let's just go with it. Uh, so I just call the standard. Okay, I still need to. If it tells me this thing one more time, I'm gonna add it to my .bash RC. So you'll see the physical robot moving, and based on that, the simulated robot will also move, and the map will get updated. So, using the green LiDAR's readings and matching the expected readings with the ones that it's actually obtained, it calculates its location, and then the LiDAR readings, like you saw right now, strike new obstacles, and it puts a black dot denoting it as an obstacle. Of course, not immediately. Once, I mean, you only call it as an obstacle when you consistently look at it. Otherwise, the false positives could result in a havoc. So it waits for enough confidence. So that's a G mapping utility. It's doing a LiDAR based mapping. Uh, the robots actually work slow. So I'm taking it on a complete tour. So that's me giving a guided tour to this robot. You actually should observe that it's actually correcting its errors in the map as well as in the location as it goes along based on how the LiDARs behave. The LiDARs will have noise. I think the map is complete, so let's just stop it. What you saw, the little bit of lag was just because Gazebo is heavy and I'm doing this thing. So, I mean, that's what you see. The teleoperation is given the command velocity to Gazebo, which is giving all the information required to the G mapping. I have to save this map so that I can use it every time the robot runs. My teleoperation is done, so let me just kill it. Let me save the map. Is there a mapping utility? Yes, there is a map server. So map server, does it have a way to save the map? Yes, map saver. That's for Turtlebot3. That's a general G mapping server. So right now I'm calling the G mapping server, which also I installed it as a library, slam library, and let me save it as a file. Map. So it's saying that it could save the map. Let me confirm it. Yes, I do have a map. So that's a visual image. It looks like the real map. There may be some errors. And this one is a configuration file which basically says the image name. Of course, in image everything is pixel and in real world everything is meter. So that's the resolution. This is where exactly is the origin and some threshold and other parameters. So that seems to be okay. That seems to be doing good. Now my mapping is done so I can close the always. I cannot close the physical real world. So otherwise I'll lose my robot. My robot will no longer be there. So Gazebo needs to run. Now let me see if there is something on navigation. So let me search for navigation. Turtlebot. There actually is. You can actually double tap and find out what all options that you have. Navigation is one of them. So double tap. Yeah, there's a Turtlebot3 navigation. Now I need to tell the robot which map file to use so that the robot has the map in its mind. So it actually invokes the map server and you with that, otherwise the map server is gone. So it invokes the map server and it calls the same map file. So I say map file is now currently, of course, you see that the LiDAR readings don't match. So, I mean, these are the current LiDAR readings, and this is the map, and the LiDAR reading should coincide with the map because every robot believes it starts from the charger, from the origin, from where it started mapping, from its home location, and we cheated. So we did not start it from where we promised to have started that up, and because of that, we had to tell the robot its position. Otherwise, it won't be able to find out. It cannot globally localize itself. It assumes it's at the origin. It's not at the origin. So this is inside robot's mind, and this is the actual robot. I think it is somewhere. Never start from any location but the charger. So now, if it was a real robot, I could have actually looked at it and found out where it is. Now I'm just trying to make a guess. It was better I would have started it at the origin. Okay, that becomes even worse. Let me do one thing. Let me just accept whatever I get. I don't have a very good control over it because there's a little bit of lag that my system is facing. So let me just accept it. With the real robots, it becomes easier. And let me just try to ask it to reach a goal. And what you see is this is the local map where it's incorporating the new obstacles as perceived by it. The current position is not great, but then I didn't start from the charger and I publish a goal. So I place a goal, and you can see that the robot using the navigation stack is automatically going to where its goal was. And here you see the physical robot going. That's the best that you can get. That's a physical robot. That's a simulated robot. The position wasn't great to start off with, and then eventually it corrected itself up. The green things that you see is what its estimate of position is. So it's using Monte Carlo localization. So these are different particles of the filter. I can change the goal again, and this is the local plan, this is the global plan, this is what the position is, this is what's the immediate motion, this is what is the sub goal, this is what is the local plans planning window, this is of course the global plans planning map. So that's all that is happening around over here. Meanwhile, as it goes along, I can always ask it to go somewhere else, and it should do that. And I act actually very funny, so as it's moving around, I quickly place a obstacle over here, and it can say that okay, there was an obstacle, and it replans itself up. So that's the global map does not have this new obstacle, the local map has this new obstacle, and using that information it has been able to sense it and avoid this obstacle. It's still accounting for this obstacle as it travels along. The local map has it, that's local planning's window, and there you see it has reached the goal. So let me give you a final one, and let me just let the robot go over here. And meanwhile, if you want to see, of course the robot is planning. Now you also have a mapping server which is providing map to the move base. You've got the localization system which is providing the location to the move base. You've got this gazebo which is taking the command velocity. /tf is a transformation library. So all these things are running in parallel. As so there's localization running, there's mapping running, there's motion planning running, there's goal which is running, there are transformations library, and the robot finally reaches out goal extremely nicely and extremely safely using only but navigation stack, which is completely, so there's no programming here, it's completely what is the implementation of navigation stack by the manufacturer. And we conclude with this wonderful graphics and wonderful simulator gazebo and the wonderful platform which powered it up, which is the robot operating system.